Welcome. In this video, we take a look at the last section of Chapter 1, 1.5 on implications. We will look at the truth of implications, truth tables, converse, inverse, contrapositive, implications in predicate logic, and we will return to Smolian's Island for an even more complicated logic puzzle. So here are some examples of implications, or also called conditionals. These are all if-then. If n ends in the digit 2, then n is divisible by 2. If n ends in the digit 3, then n is divisible by 3. If n is odd, then n minus 1 is evenly divisible by 8. If n or m is odd, then n plus m is odd. If n or m is even, then n times m is even. So some of these are true, and some of these are false, and some of these you might not be able to determine whether it's true or false. But they all have this form, if then. Now we read this as the word implies. So that arrow, I would read this as P implies Q. Or I might say, if P, then Q. P is the hypothesis and Q is the conclusion. So my hypothesis in one of these examples might look something like n or m is odd, and my conclusion would be a statement n plus m is odd. So what does it mean for an implication to be true or false? Okay, consider this. The following implication is false. X is even implies x over 2 is odd. And let's just assume, to make things easy, x is an element of the integers. We're only focused on integer numbers here. X is even implies x over 2 is odd. Now, that's false. How do you know it's false? It's false because maybe you were able to think of a counterexample. And that's exactly what it means to be false, when a counterexample exists. So in this particular case, 12 is a counterexample because 12 is even, but 12 over 2, which is 6, is not odd. So a counterexample is a value of x that makes the hypothesis true, but the conclusion false. Let me say that again. That's important. A counterexample is a value that makes the hypothesis true, but the conclusion false. And an implication is false exactly when a counterexample exists. Symbolically, this is how we would show the existence of a counterexample. There exists an x such that p of x and not q of x. This is the situation when the implication p of x implies q of x is false. All right, now curiously, analyzing true implications is a little bit trickier. This x greater than 5 implies x is greater than 0. This is definitely true. There are times when the hypothesis is satisfied. Let's see here, x greater than 5, x greater than 0. So I can use the number 7, in which the hypothesis is satisfied and the conclusion is satisfied as well. So we put the 7 here, so that's true, true. There are times when the hypothesis is not satisfied. So what about the number 4? Well, 4 is not greater than 5, but still 4 is greater than 0. So when I have the number 4, it's interesting I have a particular case of false implies true, even though I know the implication is true. What else could I have? I could have the number -3, which makes my hypothesis false, but also the conclusion false. So it's kind of curious. For different values of x, this implication could read true implies true, false implies true, or false implies false. But definitely, there's no counterexample. We will never have that true implies false. Okay, so the implication is true basically if any of these three cases works. It's true if no counterexample exists. There is no such x that makes p of x true and q of x false. Symbolically, kind of take a look at this. It's a little bit weird. I'm saying no counterexample. So it is not the case that there exists x that makes p of x true and q of x false. Now, when I distribute the negation, exists turns into for all, and this and statement becomes an or, and I distribute the negative, not p or q. And this guy, curiously, that's essentially this part of the truth table. All right, let me spell it out a little bit more clearly. Okay, p implies q. That thing is false if the counterexample exists, if p is true, so my hypothesis is true, and q is false. The hypothesis is false. P implies q. This implication is true if the negation of that, if not p or q. And that lets us build a truth table for the implication. Let's work it out. True implies true. Is that true or false? Well, let's see here. P and not Q, so no, I think that's going to be true. True implies false. There's our counterexample. That's the one situation where my hypothesis is true and the conclusion is false, so that's false. What about false implies true? Well, the implication is true if not P or Q. So actually, as long as my P is false, it's going to be a true implication. And this is what a lot of people find a little mysterious and confusing. How can you have an implication, false implies true, and that's a true implication? Or false implies false, and that's a true implication? And it's just, that's the way it is. It's just a little bit weird. The only time that P implies Q is false is when P is true and Q is false. This is the situation of the counterexample. That is the only time that an implication is false. These two cases on the bottom, yeah, they're just weird. It's hard to really believe why those should be true implications, but they are, and it boils down to the fact on the bottom here. The only time an implication is false is when there's a counterexample, is when P is true and Q is false. All right, let's move on a little bit. What if we have a situation like this? We can make a compound truth table. All right, so I want to figure out the truth value of the rightmost column. So I'll break it down and let's figure out not Q. So I will negate the Q column. False, true, false, true. And I want not P, so let's negate the P column. So false, false, true, true. And now let's do the implication. Not Q implies not P. Okay, false implies false. That is a true statement. True implies false. There is our counterexample. That's going to be false. False implies true. That's true. True implies true. That's true. All right. Oh, there is something curious about this this truth table. I don't know if you remember. Can I go back a slide? Oh, there we go. On this previous slide, the truth table for P implies Q was true, false, true, true. Okay, and here's the next slide. And the truth table for not Q implies not P was also true, false, true, true. So in fact, we have an identity here, an equivalence. Not Q implies not P is logically equivalent to P implies Q. Converse, inverse, contrapositive. These are very useful terms to know. So we start off with some implication. P implies Q. So there's our original statement. And for example, we might say, if it's raining, then there are clouds above. So it's raining is the P, and there are clouds above. That's my Q. The converse of that statement we get by just flipping around the P and the Q. If there are clouds above, it is raining. Oh, now by the way, my original implication, is that a true statement? Let's go ahead and assume that it is. It is a truth that if it's raining, there have to be clouds above. But what about the converse of that? If there are clouds above, it is raining. Well, no, our experience tells us that that is not a true statement. So that is actually a false statement. So just because an implication is true doesn't mean that the converse is true. I mean, it might be, but there's no guarantee. Just because an implication is true doesn't mean that the converse is true. This is a logical fallacy that a lot of people fall into, thinking that the converse of an implication must hold true. All right. Now, the inverse, I get that by negating P and negating Q, but keeping their order correct. So the inverse of my original statement says, if it is not raining, then there are no clouds above. And think about that. Is that a true statement or a false statement? That one's false also. In our experience, there are times when it is not raining, but there are also clouds above. And last one, the contrapositive. So with the contrapositive, what happens? I flip the order of the P and the Q from my original statement, and I negate. So if my original statement is P implies Q, the contrapositive not Q implies not P. And so that looks like this. If there are no clouds above, then it is not raining. True or false? We'll call that true. So look at this. It turns out that the original statement and the contrapositive are logically equivalent. In fact, those were the two truth tables that we just identified in the past two slides. These are logically equivalent statements, an implication and its contrapositive. So if the implication is true, the contrapositive is true. If the implication is false, the contrapositive is false. Sometimes there are problems in mathematics where the problem is stated one way and it's kind of difficult to solve, but if you turn it around and write it as the contrapositive, it gives you a little bit of insight into how to solve the problem. Now look at this, the converse and the inverse. These two are actually contrapositives of each other. If I start with the converse, Q implies P, switch the order and negate, I get not P implies not Q. So the truthhood or falsity of the converse will be exactly the same as the truthhood or falsity of the inverse. Let's take this statement and rewrite in a standard if-then form, and then we'll find the contrapositive. So a lot of times in English, we actually put the if at the end. 2n is divisible by 4 if n is even. But to flip it around, I would just say, if n is even, then 2n is divisible by 4. So there's my original P implies Q. And what's the contrapositive of that? All right, it is not Q implies not P. If 2n is not divisible by 4, then n is odd. And we'll say odd is kind of the same thing as being not even. In general, if I start talking about divisibility and if we use the variable n to represent a number, we really are just talking about the integers. How about implications in predicate logic? So the majority of mathematical statements can be written in the form, for all x in some domain, P of x implies Q of x. Here's what I mean. Here's an example. This is an example of a typical mathematical statement. For all integers x, if x is odd, then x squared minus 1 is divisible by 8. I'm not saying if this is a true or false statement. I'm just saying this is a typical mathematical statement. And maybe you can think to yourself for a little bit, is that true? Could you prove that it's true? Or if it's false, you'll need to find a counterexample. Can you find a counterexample? We negate that, and we come up with a statement, there exists an x, such that, oh, now look at this, the negation of an implication. When I negate that, That's what I get. P of x and not Q of x. This is the counterexample. A counterexample statement would say, there is some x, where x is odd, so the hypothesis is being satisfied, and x squared minus 1 is not divisible by 8, but the conclusion does not hold. So the hypothesis is true, and the conclusion is not true. All right, rewrite each of these using formal predicate logic. How might we put these into some kind of a logical symbolism? Example 1. If n is an odd integer, then n squared minus 1 is evenly divisible by 8. Well, this is essentially the example that was just on the previous slide. So we might say, for all n in my set of integers, n odd implies n squared minus 1 divisible by 8. All right, so I'm using the for all, I'm using the little arrow for implication. I'm just kind of writing it a little bit more logic-y. Oh, one thing to break up. Notice this hypothesis, n is an odd integer. Observe how I broke this up into two parts. For all n in my set of integers, n being odd. That way I got my domain and my hypothesis. How are you going to split up the domain and the hypothesis in example 2? If x is a real number less than 1, then 1 over x is greater than 1. All right, let's see here. For all x in my set of real numbers, now that's a double struck r, looks like that. If x is less than 1, so x less than 1 implies 1 over x greater than 1. At this point, see if you can negate the above two statements. See what you end up with. Pause the video, give it a try, and then start up again when you're ready. All right, let's see here. Maybe I'll give myself a different pen color to write the negation. So in the first example, the negation, how about there exists n in my set of integers such that n is odd, so the hypothesis is satisfied, and n squared minus 1 is not divisible by 8. So that's the statement of the negation. And how about in example 2, what does the negation look like? There exists some x in my set of real numbers, there's my counterexample, where x is less than 1 and 1 over x is less than or equal to 1. Those are the negations. Okay. And let's finish up with a nice logic puzzle. So these puzzles become even more devious when you're allowed to start putting implications in them. So we're on Smileyan's Island, where all the inhabitants are either truth tellers or they are liars. Truth tellers only tell the truth, the liars always lie. You can't tell them apart by just looking at them, but maybe you can tell them apart by what they say. So person A says, if B tells the truth, then I tell the truth. And person B says, if A tells the truth, then I am a liar. All right, what kind of people are these two? So once again, we can figure out the puzzle by making a truth table. And we started off by looking at the 4 scenarios by what these two people could be. Either a truth teller, or a truth teller and a liar, or a liar and a truth teller, or a liar and a liar. And analyze A's claim and analyze B's claim. Is the claim true or false? So pause the video for a second, really give this thing a try, fill in that table and see if you can figure out A and B, what kind of people they are, and when you're ready, unpause it and we'll see how we did. All right, so A's claim, let's focus on what A is saying. A says, if B tells the truth, then I tell the truth. So we're kind of going this B implies A direction. If B tells the truth, then I tell the truth. So we're really sort of asking, true implies true. Is that thing a true? And that is a true statement. how about false implies true? Well, you know what? That's actually also a true statement. That's okay. True implies false. Oh, there's my counterexample. I can't have that. Oh, and just to see, let's compare that with A's statement. A says, if B tells the truth, then I tell the truth. But this situation has B telling the truth and A being a liar, so that can't hold. And then finally, false implies false. That is a true statement. At this point, let's analyze B's claim. So B says, if A tells the truth, then I am a liar. So basically something like, let's see in shorthand, A implies not B. So, looking down at their character, truth implies not truth. So true implies false. True implies false. Is that true or false? That is the counterexample with the true hypothesis and the false conclusion. So that is the false statement there. How about true implies not false? So true implies true. That is a true implication. False implies not true. So false implies false. False implies false is a true implication. And lastly, false implies not false. So false implies true. That is also a true statement. Okay? At this point, where do the character of A and B match with the claims of A and B? And it looks like there is one row. Scenario 3. So it has to be the case that A is a liar and B is a truth teller. And you can take a look at those two claims on the top and just sort of convince yourself that yes, indeed, that is the scenario that actually works for these two people. All right, and that concludes section 1.5, and in fact, it concludes chapter 1.